Welcome to video 1 on fancy adding. I'll start by providing some motivation why we need fancy adding. I have this character named Mike who wants to invest $200 per year, and this investment is going to grow at an annual interest rate of 6%. The question is, what will the future value of these investments be 10 years from now? So I'll describe a little bit more about what the problem is asking. In year 1, Mike's going to throw a pile of money into an investment, and it's going to have a future value. I'll call it A for amount, which will be equal to the principal times 1 plus the interest rate R to the power of 10, because it's going to be invested for 10 years. This is a formula from the unit on exponential functions. It was described as the model for investing money at a fixed interest rate R that is given annually and compounded annually. I'm going to call this A1 for amount 1 and P1 for principal 1. An important note with interest rates is that a 6% interest rate, percent means out of 100. So we're going to have to do that, we're going to have to write R as 0.06 and not as 6. Okay, so I'm going to plug that in. I'm going to plug all the numbers in. 200 is our principal that we're putting in. 1 plus 0.06 is 1.06, power 10. And then the number that comes out of that is a task for a calculator. In year 2, we're going to throw a pile of money in. So amount 2 will be principal 2 times 1 plus R to the power of not 10, but 9. Here's why it's 9. Because the question is asking what will the value of the investments be 10 years from now. And if we put another $200 in next year, then 10 years from now, that pile of money will only have been invested for 9 years. It doesn't get that first year of investment. That's this year, because we haven't invested it yet. Okay, now plugging in the numbers, we're going to have 200 times 1.06 to the power of 9. And then we could continue year 3, year 4, year 5, 6, 7, 8, 9, and 10. So A3 will be P3 times 1 plus R to the 8. So 200 times 1.06 to the power of 8. A4 will be 200 times 1.06 to the power of 7. See how it's working out? There's a pattern to these. But etc. And then the total value is going to be, I'll do it down here. Total is going to be A1 plus A2 plus A3 plus ... all the way up to A10. That would be how much money the total investment is worth in 10 years. So this question combines some knowledge of exponentials, the exponential growth model. It combines adding a whole bunch of individual investments together. And it's a very tedious calculation to do, even if it's only 10 years. Now imagine this calculation repeated with a compounding period of 1 month, annual interest rate of 6%. Over a 10-year period, we'd have to do this 120 times, 12 times for each of the 10 years. Each of those calculations is fairly simple to do, but there's just so many of them. And what I'm going to show inside this series of videos is a set of shortcuts that can be used to add more efficiently. Well, the topic of fancy adding is fairly important. Far, far more important than trigonometry and some other topics that find their way into calculus courses. It's a standard topic. The topic of summations is fairly standard to come across in Calc 1000, 1301, and it's likely to be one of the things that you bring with you into your courses next year, whether those are finance courses or actuarial science courses. You know shortcuts for adding already. You were introduced to them a long time ago in elementary school. For example, the idea of adding up the number 3 to itself 10 times, 3 plus 3 plus 3 plus 3, and so on 10 times. What you learned when you learned about this way back when was that this is the same thing as multiplication. This is 3 times 10, which is 30. And we learned this as a quick way to do sequential addition. And eventually we just treated it as something to memorize, that 3 times 10 is 30, instead of adding up 3 to itself 10 times. Now this isn't the only shortcut that exists for adding. This is adding the same number to itself some number of times. We also have shortcuts for adding up different numbers a certain number of times. So for example, we have a shortcut for adding up the first 10 numbers, or the first n numbers. Now you can try this out on your own. Explicitly add up 1 plus 2 plus 3 plus ... up to 10, and what you'll get is you'll get 55. And it doesn't take long. It's only 10 numbers. But even though that's relatively simple to do, it's not so simple to add up the first 1,000 numbers. Any pair is fine to add, but it's just time-consuming, tedious, and you'll probably make a little mistake at some point. Add these first 1,000 numbers together. What I'll show you is that there's a shortcut that will work for the sum of the first 10 numbers, the sum of the first 1,000 numbers, or the sum of the first n numbers for any general number n. And I'll prove the following shortcut to you, that the sum of the first 1,000 numbers is 1,000 times 1,001 divided by 2. In the same way that the sum of the first 10 numbers is 10 times 11 divided by 2. And that the sum of the first n numbers will be n times n plus 1 over 2. And this formula was discovered a few hundred years ago by a fellow named Gauss. And Gauss was in grade 5, I believe, when this happened. But the story goes that his teacher was punishing him for being a bad boy in class, and his punishment was to add up numbers. So your punishment today is add the first 50 numbers together and tell me the answer. And eventually he came up with this formula, this shortcut, and the teacher called his bluff and said, I don't believe it. I think you're just making up a formula that worked for that one problem. And it was shown very quickly that he was right. And he went on to become a famous mathematician. But I want to prove to you that that actually works, that the sum of the first n numbers is n times n plus 1 over 2. And the proof formulation I'm going to use is called a direct proof. And it's kind of cute. I'm going to start by saying our goal, the sum that we're interested in, I'll give it a name, I'll call it S. And it's going to be equal to the sum of the first 10 numbers, 1 plus 2 plus 3 plus 4 plus 5. I'm going to explicitly write them all, even though we don't need to, as you'll see, but it's a good idea anyway. And actually, I'm a liar. I'm not going to write them all because I want to solve the harder problem. I don't want to add the first 10 numbers together. I want to add the first n numbers together. So ... all the middle ones. At the very end, the last number we're going to add is n. Now let's think about what the second last number is. If n was 10, the second last number would be 9. Since I don't know what n is, I want to leave this very general. Our second last number is just going to be n minus 1. 1 lower than n. And the number previous to that is n minus 2. A neat thing about addition is that the order of addition does not matter. So for example, you know that 7 plus 6 is the same as 6 plus 7. Doesn't matter that you have the 7 in front or the 6 in front. It makes no difference. Both 13. And I'm going to exploit that fact by writing S in a different order. I'm just going to reverse the order of the sum. So I'm going to start with the last number, n, then write the second last number, then write the third last number, and then dot, dot, dot. And we have plus the 5, plus the 4. And I won't even write those ones. I'll just write the first 3. So plus dot, 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 plus 3, plus 2, plus 1. So the dot, dot, dot contains the 4 and the 5 and the 6 and the 7 and all the other numbers that are in between. So, and again, the reason why this is true, this is still equal to S, is because the order of summation does not matter. Next thing I'm going to do is I'm going to add these two equations to each other. So I'm going to add equation 1 to equation 2. On the left-hand side, they're both equal to S. So S plus S, we get 2S. On the right-hand side, we get 1 plus n plus 2 plus n minus 1. So what I'm doing is I'm adding them in columns. I'm adding this together, so 1 plus n. I'm adding this together, so 2 plus n minus 1. I'll go to the next term in the sum, the next pair of terms, plus bracket 3 plus n minus 2, plus, there's some terms in the middle they're going to add, dot, 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 and I'll just look at the last 3. We have n minus 2 plus 3 plus n minus 1 plus 2 plus, and the last pair is n plus 1. I'm going to simplify. 1 plus n is the same as n plus 1. 2 plus n minus 1 is the same as n plus 1. 3 plus n minus 2 is the same as n plus 1. Wait a second, these are all n plus 1s. And how many of these do we have? So looking at the original, at that first line, we have n terms in our sum. 1 plus 2 plus 3 all the way up to n. So that means we have n of these. And you know that if you add 3 to itself n times, you're going to get 3 times n. If you add n plus 1 to itself n times, you're going to get n plus 1 times n, or n times n plus 1, same thing. So 2s is equal to n times n plus 1. Now we can divide both sides by 2, so the sum s is equal to n times n plus 1 over 2. There you have it. There's your summation formula for the sum of the first n numbers, independent of what that number of numbers is, independent of what n is equal to. Okay, so that's kind of neat. When was the last time you learned something new about adding? May have been in grade 1, maybe grade 2. In addition to learning shortcuts for doing addition, one of the important things we're going to learn in this section is a piece of notation that will come up in your actuarial science and finance courses, and that notation is called sigma notation. The weird looking symbol here, I'll outline it in purple, is called the letter sigma. It's a Greek letter. This is the capital sigma. And it means sum, it means adding. And there's a few pieces of anatomy of this object. The first piece of anatomy of the object is something called the index. I'll circle that. So K is the index. And it plays the role of something like x in a function. It's like a variable. And the equals 1 part, the 1 in this case is the start of the index. I'm just going to add a little note here that K is like, it's like a variable, it's like x. Okay, and then the n is the end of the index. and f of k is just a function. It's like f of x. And so that's a function of the index k. And we note in all of this, but unlike x, unlike the variable x, we allow k to take only integer values. So 1, 2, 3, dot, 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 and not 0.5, square root of 7, etc. So the k, the index k, has to be an integer, has to be a whole number. And what it refers to, so this mysterious looking k thing, is just what number are, what if we were to label each of the things we're adding up. K equals 1 is the first thing we're adding. K equals 2 is the second thing we're adding. K is equal to 3 is the third thing that we're adding. It's just labeling, kind of like an inventory number for the terms that we're adding together. So the sum from k equals 1 to n of f of k would be f evaluated at 1 plus f evaluated at 2 plus f evaluated at 3 plus dot, dot, dot plus f evaluated at n. So the top line that's there. It's just a compact way to write a sum. Now, in order to write a sum like this, the things that we're adding together have to be related to each other through the function f. We have to be able to express them as a function of the index. So here's one example of a function. F of k is equal to k squared. Sum from k equals 1 to 4 of k squared. And we could disentangle that or rewrite it as the first value of the index, so k is equal to 1 squared, plus the second value of the index, k is equal to 2 squared, so 1 squared plus 2 squared plus 3 squared plus 4 squared, and then simplify. 1 plus 4 plus 9 plus 16, and we get 30. And it turns out there's a shortcut for this as well, that the sum of the first n squares, the first n k times k's, is n times n plus 1 times 2n plus 1 over 6. There is a way to prove this geometrically. There's not a neat way to prove this that I'm aware of that's similar to the previous proof. I think the simplest proof is to prove this by what's called induction. And that's not something I'm going to do. So if you're interested, you can Google search the following: proof by induction. For sums. If you're interested, you don't have to do this. This is optional. You could Google search that or go to YouTube and just search that directly, and you'll find a proof by induction for the summation formula. I'll erase that because I don't want you to worry about that. There's tons of these formulas. There's tons of different summation shortcuts because summations are actually important. So here's another one, a sum of fractions. And you would know how to do this if you had to. 1 over 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16. You'd have to make common denominators. So 16 over 16 plus, like it's yucky because it's fractions, but it's not impossible. Even though it's possible to do it, I don't really want to do it. Imagine if there was more terms, like 1 over 32, 1 over 64, 1 over 128. It gets worse and worse and worse. And rather than add that up, we could imagine solving a slightly harder problem. The sum from k equals 1 to n of 1 over 2 to the power of k minus 1, which looks really strange, but let's break it down. So this notation, k equals 1 means that's where we're starting our sum. So the first term in our sum is going to be what we would get if we replace the k in this expression with 1. So 1/2 to the power of 1 minus 1, which is 1/2 to the power of 0. Then we go to the second term in our sum. So k is equal to 2 is the second term. we're going to have 1/2 to the power of 2 minus 1, which is 1/2 to the 1. And do it again. Okay, now the next term is 3. K is equal to 3, so we're going to have 1/2 to the power of 3 minus 1, which is 1/2 to the power of 2. So that's our third term of the sum, and we just continue on till we get to the nth term. So the top number. Oh, and I have a typo here. A little mistake. That's okay. Fix it. This is going to be an n minus 1. So we're just replacing that k with an n. So that would be a way that we could express the sum that's above more generally. So the sum that's directly above would be the first 4 of those. But we could continue the process and figure out what the sum would be if there were more pieces, if we could find a way to express this more general formula. And actually, that harder problem, let's make it even harder. Because counterintuitively, and this is a thing that's common in mathematics, when you go to solve an easy problem, or when you go to solve a relatively easy problem, like the very first one, sometimes the easiest way to solve a problem is to make a harder problem, find the solution to that problem, and then solve your original question as a special case of your general solution. And it's a situation that repeats itself many times in mathematics. So the harder problem I want to look at is the following. The sum from k equals 1 to n of a times r to the power of k minus 1. So what this might look like, to make it look a little bit less mysterious, would be the sum from, let's say, k equals 1 to 100 of 3 times 2 to the power of k minus 1, something like that. I want to add up the first 100 of those. So the first few of them, we'd have 3 times 2 to the 0, plus 3 times 2 to the 1, plus 3 times 2 to the 2, plus dot, dot, dot. And we'd have 3 times 2 to the 99, would be the last one. So I want to find a way to do that efficiently. And I'll start the derivation of the formula for adding this up quickly as a shortcut. I'll show that formula and the proof of that formula on the next video.